Okay, welcome everyone. Let's start with the third lecture. Let me say up front that I don't have as many slides as I had the other days, so we'll see how long it takes for me to explain to you how large-scale structure works in the universe, because I ran out of time a little bit. But anyway, I will try to explain to you what the large-scale structure of the universe does. Yes, it is working. So I'll first, of course, briefly summarize where we are so far with the lectures. And I will try to give you a feeling for the physical sizes that are relevant in large-scale structure formation that I'll be talking about. Then I will briefly repeat linear perturbations that we saw yesterday and try to explain how that turns into the matter power spectrum that we observe in the galaxies. Actually, I will not say anything about the mildly nonlinear spectrum, but I will try to explain how computations of the nonlinear formation of structure work, which is done in simulations. And then there's one slide on variant oscillations and 2 slides on re-glancing. I would have liked to go into much more depth with weak lensing, because that is the main observable of the LSST experiment and the Euclid satellite and many other future large-scale structure surveys, but not sure that we can do that today. So, where are we so far? This is a picture that I haven't shown yet, but this is our universe. I didn't realize that. Exactly. Here it comes again. So, you are here, in the center of the universe. And you truly are in the center of the universe because our observations are on the past light cone. We only have 2 angles and the redshift of the photons that we receive and the brightness. And we cut the photons into, and we use the redshift of the photons as the radial coordinate in our coordinate system. And it means we really observe a sphere in everything that is farther away from us is at a higher redshift and is at a time farther back in the past. So you are in the center of the universe and we're looking out at different redshifts. So to give you an idea of what these different values of redshift mean. Well, first of all, it fell off the slide. Redshift is of course the ratio of the wavelengths as emitted and as observed. In a homogeneous universe, this is directly related to the size of the universe. If the universe doubles in size, the wavelengths double in size, so the energy of the photon decreases by a factor of 2. So redshift 1 means that the universe is half the size it is today, 1/3, 1/4, 1/6, 1/8, and here it's 1/1100th of the size it has today, 1/1100 Supernovae, for example, the key observation that proved the existence of dark energy, or at least that certainly falsified the Einstein de Sitter universe. I should specify that falsify a homogeneous universe with only dust. So supernovae are falsification of that, and therefore we need dark energy because only dust doesn't fit the data. They reach out to a redshift of at most 2. So when you look at the evidence for dark energy, you're looking at redshifts between 0 and 2. And that is a distance of 3.5 gigaparsecs over h. Small h is the Hubble rate, so the expansion rate today, in units of 100 kilometers per second per megaparsec. So with the observations of the Planck satellite, for example, this value h is constrained to be approximately 0.68. So by all means you can pretend that this is a factor of 0.7. So that's how this scales. A gigaparsec, to remind you, is 10 to the 9th times 3 light years. 1 parsec is about 3 light years. So supernovae reach to about 3 gigaparsecs. The farthest radio galaxy, I think I've done something wrong with the resolution of the projector because the slides are the farthest radio galaxy is at the redshift of 5, which is 5 gigaparsec. Where the quasar, redshift 7, is only 6 gigaparsecs. And you see how redshift does not scale linearly with distance, because redshift of 50, which is 10 times as high redshift as redshift of 5, is only 1.5 times as far in common distance. It's because the universe is expanding. So different. If you go at a higher redshift, the universe is smaller and smaller, and you cannot travel an infinite distance, because the redshift of infinity, which is basically saying where the universe was infinitely small compared to the size it has today, the distance at which that lies from us is a finite distance. So in principle, it should be possible to see the Big Bang if the universe had not been opaque after the Big Bang. So redshift infinity lies at a finite distance, which is actually very close to this value. And that effect is the horizon. In an expanding universe, you can only see, you can only look at a limited distance. However, when you look at galaxies, then the volume that you can probe in terms of redshift is very small compared to the maximum redshift that you can observe in the universe. These two red lobes are projections of all the galaxies observed in, for example, Sloan Digital Sky Survey. And the LSST will observe a similar reach in redshift, possibly farther. It may go up to redshift of 1, but galaxies really are not visible at higher redshifts. So I did unfortunately not put here what the redshift is, but this actually goes to the order of 1 gigaparsec.
Where is the formation of stars and the formation of galaxies?
That's a good point. Well, I mentioned in the lectures on the cosmic microwave background that the universe reionizes at the redshift, which is not very strictly constrained, but between redshift 6 and 10. And it reionizes because stars start forming and emitting high energy radiation. So it's I guess you could say that it's close to the blue band where stars and galaxies start forming. I'm quickly going to change the resolution of the display because things are falling off. There we go, now everything's on the slide again. I went back on slide, so here we go again. There you are. Sorry about that. Did I say everything I wanted to say about this slide? I think I did. So the quest in cosmology is about understanding the space-time of the universe. And the space-time of the universe is probably described by Einstein equations. We want to understand if Einstein's equations are correct, so we want to test the theory of gravity that describes the space-time, and we want to figure out what is the matter that goes into the space-time of our universe. And the first piece of information that we have access to that can help us to constrain the space-time is the expansion rate, and another observable which is depending on the integral over the expansion rate, which is all distances as a function of redshift in a homogeneous universe. This was the first lecture. So if you measure the redshift of an object and given, for example, the intensity of the light that we observe from that object, you can compute what the distance to that object is. Or if you cannot have access to the intensity of light, but you know its original physical scale and you see its angular scale, you can also compute the distance. These two are related by a simple factor. Then you have the redshift and the distance to an object, and then if you manage to measure that at different redshifts, you're sampling this function at different redshifts, so you're actually sampling out the borders of this integral. And therefore, if you want to explain your observations, you need to tune these parameters that go into this integral, which is the cosmological constant, spatial curvature of the universe, radiation density, and the matter density of the universe, to fit your distances. And inversely, that means that if you observe these distances, you can constrain what the matter content of the universe is. That's the first thing you have access to in cosmology. We have this measured very accurately, this function, and therefore there are tight constraints on all these parameters, and they're all, so the matter and radiation and cosmological and dark energy density are all constrained to be non-zero, and the spatial curvature of the universe is in fact constrained to be very close to zero. But there's still some wiggle room. There's still the possibility that the universe has some spatial curvature. It means that hypothetically, if you would walk infinitely far, you would end up in the same spot. Of course, when you say that you're ignoring the fact that the universe is expanding and will contract again, but if it's spatially closed. So that was the first lecture. The second lecture was on the cosmic microwave background. I explained to you that this rugby ball is a projection of the sky, and if you take the Fourier transform, or actually because it's on a sphere, you take the spherical harmonics transform, you get a measurement of the power spectrum in that image. And I explained to you how this power spectrum is not exactly the same, but it's very closely related to the correlation, the distribution function that describes the distribution of these temperature spots. So this function is, the observations measured as pseudo-CLs, which are closely related to the spectrum that generated the initial perturbations. And this spectrum that generated the initial perturbations gives a correlation, but we only measure one picture, so therefore we can only guess that it's the correlation that led to this spectrum. So we have the CMB spectrum with the different angular peaks, and we saw yesterday that each peak corresponds to a certain phase of the oscillations of the baryon photon fluid. And we saw that the first and the third peaks correspond to phases of the oscillations where the dark matter overdensities and the baryon photon overdensities are in phase with each other, are exactly aligned. That's where you get the maximum peaks. And the even peaks, so the second and the fourth and the sixth, etc., are peaks that correspond to phases in the oscillation where the dark matter, which is not oscillating, is still in the same place, and the baryon and photons are in the opposite phase. So the overdensities of photons and baryons are in the positions where the dark matter is underdense. And that's how we saw that if you change the amount of baryons, for example, you can change the relation between the even and the odd peaks. You will change the height of the second and the fourth peak compared to the first and the third. That's how the CMB constrains the baryonic content of the universe. The overall amplitude says something about the dark matter content of the universe. So I hope I convinced you that the CMB alone already gives very tight constraints on the presence of dark matter. You cannot fit the CMB without dark matter. You don't get this peak structure. One third quantity that we can relate to this is the fact that we observe the CMB, these peaks, at different angular scales. Given the content that goes in the CMB, we know what the physical distance was to which this angular scale corresponds. So we observe an angle, we know what the physical size of that object is that we observe under that angle, so we compute the distance. We can compute the distance to that surface. And therefore the cosmic microwave background constrains the distance as a function of redshift, so also the expansion rate of the universe. So the ratio of the peaks gives you the relation between baryons and dark matter. The height of the peaks gives you the amount of dark matter, and also the primordial power, the initial power spectrum that seeded the perturbations, which I did not say anything about, but I will address that tomorrow. The overall angular position of the peaks gives you a hold on the age of the universe, because the expansion rate is directly related to the age of the universe, and spatial curvature. The lensing of the CMB power spectrum, which is most, in this figure, would be most visible at much higher multiple moments, so above the right hand side of this figure, gives you a handle on dark energy. Nowadays you cannot fit the cosmic microwave background anymore without dark energy. The CMB spectrum is damped by the reionization of the universe at redshift 6, so the CMB gives a constraint on the time, on the epoch in which stars form. So the Zalovich effect shows spots in the directions of clusters, hot gas clouds in the CMB, which gives another extra constraint on the dark matter density. And there are more observables in the cosmic microwave background that we have not discussed yet. For example, I will try tomorrow to explain a little bit about polarization, because I think that fits better in a story about inflation, because it's closely constraints that we can give on inflation are closely related to polarization. I've mentioned various distances that exist, and I want to show you this plot, which is a logarithmic plot of the redshift on the horizontal axis and the distance on the vertical axis. And the different colors, I hope you can read it. The orange line is the angular diameter distance as a function of redshift. So that tells you roughly the angle under which you observe an object of a certain size. And what's funny is that the angular diameter distance has a maximum and then goes down again. If you go to, say, redshift infinity, so the Big Bang, you put an object there of a few centimeters width, and so no, you put a correlation there with a few centimeters width. So you put two particles, a few centimeters apart. You let the universe expand, and it's redshift infinity, so now they're infinitely far apart. Today they're infinitely far apart. On our observable sky, they're somewhere between infinite and a finite width apart. Because of the expansion of the universe, we observe them under some large angle. But their physical size, the separation between the two is only a few centimeters at the Big Bang. So you understand that this ratio goes down at very large redshifts, because the smallest object is observed at the largest angles. So the angular diameter distance has some non-trivial feature in it, the fact that it has a maximum and then goes down again because of the expansion rate of the universe. And nearby, clearly, the angle under which you see a physical object should shrink if the object is farther away. So nearby it just works the way you intuitively expect. Related to the angular diameter distance is the luminosity distance, which is the angular diameter distance times 1 plus redshift squared. Because it also measures the rate at which an object will stretch on our sky through the intensity of light that we receive from it. So now if you let this centimeter large object emit light and expand it infinitely, it still spans a very large, an infinite angle on our sky, but the amount of light that we receive from it is also diluted by an infinite factor. So for luminosity distance, the luminosity distance does keep growing with redshift, because the farther away an object is, the less light we receive from it. And in between is the coordinate distance, which is an artificial thing, because that's not observable. That's just a mathematical construct. Coordinate distance as a function of redshift tells you not what the observable distance is to it, but what the distance is between here and that point today. But that's actually a distance that is outside of our light cone. Because we're talking about a spatial separation. We're talking about time equal to 13 billion years after the Big Bang here, and time equal to 13 billion years after the Big Bang there, and we're relating the distances between the two. But this is not physically accessible. But that is what this line is, and you see that this tends to a constant, and that is exactly the horizon. That is the fact that in an expanding universe you can only observe to a finite distance. Okay? Just to make that point clear once more. And the reason that I talk about distances is because now I want to give you a handle on the scales that go in large-scale structure formation. For example, these are my rules of thumb, the things that I keep in mind to relate distances to physical objects. The size of galaxies is of the order of kiloparsecs. 1 parsec is 3 point something light years, 3.026, etc. You can ask Google. Google knows parsecs, so if you do conversions, you can use Google and it gives you it in kilometers if you want to know, or light years. Galaxies are of the order of kiloparsecs, so also our own galaxy, the Milky Way, has a size of the order of kiloparsecs. Clusters of galaxies, so large groups of galaxies, have sizes of the order of megaparsecs, so like 1,000 more. And I showed you previously how these relate to redshifts. Let's see, am I going to show that again? No, I'm not going to show that again. So Oh wait, well, just the previous slide, of course. So you see on this slide that, for example, these are megaparsecs. So the order of 1 megaparsec, no, this is probably 10. No, well, I don't know. The order of 1 megaparsec is somewhere over here, so that's still actually a very low redshift. So if you observe objects at the order of distance of a few megaparsecs, there will be some redshift in the light that you receive, but it will be much less than the moment. So the distance relation is actually still linear. And that's why in astronomy, where you observe objects at these distances of the order of megaparsecs, you can safely assume that the expansion rate is a constant, because you're staying at very small redshifts. The expansion rate is a function of redshift, h of z. You can safely Taylor expand that. You can say the expansion rate, the size of the velocity of objects is simply the expansion rate times redshift. It's in linear regime. So the sizes of clusters are over here, which is the linear regime of the expansion rate. And so I hope that now I've given you a feeling for the distances in the universe. And the previous slide with redshifts shows that we can go to gigaparsecs when we talk about the distances to supernovae. But galaxies are really nearby in the universe. It's the late universe. Okay, now let's discuss how the distribution of galaxies in the universe arises. The point is that we only observe light. We have no idea where the dark matter is because you cannot see it. We wish we could. And we do want to know how the matter is distributed in the universe. For several reasons. Simply we want to know what the matter content of the universe is. So if you know how it's distributed, you have access to its quantities. But secondly, structure forms under the influence of gravity. And we want to test if the theory of gravity is sufficient to describe the evolution of the entire universe, or whether we need to modify gravity at very large distances, for example, or whether we need other matter components to describe the universe at large distances. So if we can describe how the matter distribution in the universe evolves, we have access to a lot of information. We have seen in the cosmic microwave background that the very early universe, at redshift 1100, when the universe was only 1/1100th of the size it has now, the perturbations in the densities are linear. Because with the cosmic microwave background, you really observe the gravitational potential we saw yesterday. So the variance in the differences in the gravitational potential are tiny, varying from different places to different places. And the model describes that structure then forms from these linear perturbations. You start with a fluid, with linear density perturbations, and of course, under the influence of gravity, the overdensities will start accumulating more and more matter. So the linear perturbations grow under the influence of gravity. So linear perturbation theory for the distribution of matter in the universe is very much the same as the cosmic microwave background. But that describes us where the dark matter is and where the baryon fluid is. It doesn't yet say anything about galaxies. Now the important assumption is that at least on the large scales, galaxies do trace the underlying large-scale matter distribution. In other words, the assumption is that galaxies form mostly in overdensities of all the matter in the universe, and that less galaxies form in the underdensities of all the matter in the universe. So if you map out the positions of galaxies in the sky, the assumption is that thereby you map out the total matter distribution of the universe. So, very much the same as the cosmic microwave background. The cold dark matter clusters, density perturbations in cold dark matter grow. Before the photons decouple, so at redshifts higher than 1100, when the universe is hot dense plasma, baryons have pressure because they decouple with photons. There's a baryon photon plasma, and the baryon photon plasma oscillates between overdense in one place and underdense in the other place, and the opposite phase. As soon as the photons decouple, so when the baryon photon plasma cools down because of the expansion of the universe, and it goes below a temperature at which photons and baryons are no longer coupled. There are no more photons to put pressure in the baryon photon plasma, so the baryons have no more pressure. And after the CMB decoupling, therefore, the baryons are just massive particles that fall into the overdensities of the fluid under the influence of gravity. Okay? So you have a oscillating plasma, photons decouple, and everything just collapses without pressure. Up to the point, of course, where you're no longer talking about linear perturbations, but where the baryons reach such high densities that they, again, heat up and form a plasma, like in galaxies. But that is not linear perturbation theory anymore. So, these 2 points are from the previous slide: cold dark matter clusters, baryon cluster pressure, and spike cold dark matter when the photons decouple. And here are 3 ingredients which are, in a sense, speculative when it comes to large-scale structure formation, because we want to use large-scale structure formation to constrain the presence of these 3 ingredients. The first one is the massive neutrinos. We know from oscillations, from neutrino oscillations, that neutrinos have masses. We know from nuclear physics that when you have a baryon photon plasma, there must be neutrinos present as well. So there is, given our physical model, there is a strong prediction that there is a large abundance of massive neutrinos in the universe. And they have a special influence on large-scale structure. They're very particular particles. I will explain later in a few more words how that works, but the point is that on large scales, the neutrinos for cluster formation behave like massive particles. And for small scales, because their masses are so small and they have large thermal velocities, they behave like massless particles. So, from this statement, you can already guess that neutrinos have a characteristic effect on the large-scale structure formation, namely that on small scales you have less massive matter than on large-scale perturbations. Dark energy, which accelerates the expansion of the universe at late times, has then intuitively an effect of slowing down the clustering of dark matter, because the expansion pool is slightly larger. However, it is possible that dark energy is a fluid itself that can cluster, and that has non-trivial effects. So, if you can observe such effects, that gives constraints on dark energy. And closely related to dark energy and clustering of dark energy are modifications of gravity. It speaks for itself that when you modify gravity, you may alter the formation of structure in the universe, because it forms under gravity. Modify it, you modify formation. So, in equations, here's the same equation as yesterday, except that I eliminated the different fluid components, and I just write down its effect on the gravitational potential. Phi is the gravitational potential. W is the equation of state of the dominant fluid that gives rise to the gravitational potential. And K is just a wave number. This is for this bit. So this equation works for different ages in the universe. When it's filled with a baryon photon plasma, it is overall roughly a photon fluid with a relativistic fluid with W equal to 1/3. At later times, when the photons decouple and their energy density drops below the energy density of matter, the most important ingredient that gives rise to the gravitational potential is dust. W then is equal to 0. It's the same equation. However, regardless of W, if K is much less than this character H, which is simply the time derivative of the scale factor, so it's a measure of the velocity of expansion. When K is much, it's true. If K is much smaller than H, of course, this equation is independent of K, and the solution is trivial, namely that phi is a constant. It will be a different constant depending on the value of W, but for all possibilities of the value of W, phi turns into a constant when K is much smaller than H. And tiny wave mode K, of course, is a very large physical distance. This relation says that when the wave mode is larger than a particular radius, which is given by the expansion rate, and that is the Hubble radius, then the gravitational potential does not evolve, it's constant. That's a direct outcome of this equation. And to remind you, this equation comes from the Einstein equations when you plug in a homogeneous metric with a tiny perturbation, the potential. This is a slide from yesterday to remind you what the energy content of the universe is, because in this equation you see W, so you need to know what is the energy content at a particular time. On the horizontal axis we have redshift, on the vertical axis we have the relative abundance of these different matter components. At high redshifts, radiation is the dominating component, but radiation redshifts as 1 over the as a scale factor to the power 4. So it dilutes faster than matter, which only scales as the scale factor to the power 3. So at some point, matter is the dominating ingredient in the universe. However, matter also redshifts. The energy density dilutes with a factor 8 to the power 3. And at some point, the energy density of dark matter goes below the energy density of dark energy, which is a constant. So at different epochs, radiation dominates, matter dominates, dark energy dominates. W is equal to a third, W is equal to 0, and W is equal to 1. Here, though, the dark matter density at times close to today is not yet sufficiently 0, so you cannot say that it's exactly -1 today. It is a mixture of the two fluids. So if we look on small scales below the Hubble radius, so where the gravitational potential can grow, in the case of radiation domination, we saw yesterday that this equation gives rise to an oscillatory solution. The gravitational potential is some sinusoidal function. And the argument of the function is wave number times conformal time tau, which is just a redefinition of your time parameter, which tells you that for each wave mode there will be a time when tau becomes large enough that it enters in this oscillatory regime. Now at later times, when matter is the dominating ingredient in the universe, W is 0, which is the equation of state of matter, because there's no pressure, so the ratio of pressure to energy density is 0. Then this equation simplifies, and there is the solution that the gravitational potential is constant, and there's the solution that the gravitational potential decays in time. It's linear perturbation theory, so the solution is a superposition of these two, and if you wait long enough, the decaying component becomes negligible compared to the constant component. So, of course, you only focus on the constant gravitational potential component. Okay. Here we have a slide that shows the evolution of the gravitational potential in Fourier space for 3 different wave numbers. On the horizontal axis we have the scale factor, which is related to 1 over the redshift. So small scale factor is a tiny universe, is a very high redshift. Large scale factor is close to today. The scale factor is actually equal to 1 today. And on the vertical axis we have some rescaling times the gravitational potential. Let's first focus on the mode that is here plotted in the bottom. This is for a large wave number. This is a wave number for which that is so large that the scale is small, which means that it comes inside the Hubble radius already when the radiation is the dominating component of the universe. Because to remind you why I'm talking about the Hubble radius is because there, for each mode, there is a point in which it transits from k smaller than the expansion rate to k larger than the expansion rate. Because the solution of this function is always a function of k times tau. So for each mode, there is this, each mode travels through super Hubble, Hubble radius, sub-Hubble. Each mode starts at very large Each mode starts outside the Hubble radius and is constant in time. And then as the Hubble radius grows in time, the mode comes inside the Hubble radius and it enters the regime where there is a time dependence in the equation. So now depending on when it enters, this is, if we talk about a small mode that enters during radiation domination, it will enter in the oscillatory solution. A mode that enters at a later time, so a smaller value of k, larger distances, it re-enters the Hubble radius at a later time. It enters when the gravitational potential is a constant. So they will behave differently. The mode that enters the Hubble radius before radiation and matter exchange their roles, so before matter takes over the driving of the expansion rate from radiation, this mode starts with as a constant in time. It enters the Hubble radius, so the solution of the differential equation transits from the constant solution of super-Hubble scales to the oscillatory solution of sub-Hubble scales. It will oscillate in time, and then at some point, equality denotes time when radiation and matter are equally abundant in the universe and when matter takes over the expansion rate. So the solution of the differential equation also transits from the radiated oscillatory solution to the matter-dominated constant solution. It becomes constant. There is a k which is called k equality, which is the mode that exactly enters the radius when matter and radiation are equal. So that is that's the separation between these two types of modes. And then there's the mode that is only re-entering the Hubble radius when matter starts dominating the expansion rate of the universe. This mode has been outside of the Hubble radius when the sub-Hubble scales were oscillating. So this mode never saw any of the oscillations because it's simply too far apart to communicate between two ends of the mode. It's too far apart to have any pressure going along that mode. So super-Hubble, it doesn't oscillate, it's a constant solution. And only after matter takes over the expansion rate from radiation, this mode re-enters the radius. And we saw already that in the matter era, the gravitational potential becomes a constant of time. So there are different types of modes in the gravitational potential depending on the physical size. And what's important is the relation of their physical size to the Hubble radius at the time when the universe transits from radiation dominated to matter dominated. Modes that are at a larger k, so smaller scales, go through the oscillatory regime, and modes that are at a smaller k, so larger scales, they never oscillate and they enter at a later time. Now I've been talking about the gravitational potential, but the question is, of course, what do we really observe? We observe light. And light is emitted by baryons. And these baryons are in stars, in galaxies. These galaxies are hopefully tracing the total matter field of the universe. So, talking about it this way, we don't observe the gravitational potential, but we do observe something that traces the matter density of the universe. So what is more relevant than the gravitational potential is, of course, the matter perturbations, and they're related to each other by the Poisson equation. So this is the Laplacian of the gravitational potential. This is the average matter density, and this is the matter density perturbation dimensions. Here's the scale factor squared, Newton constant, pi, 4. And the gravitational potential, for example, in the matter-dominated era, on small scales, as long as it's in a linear regime, is constant. As we saw previously, when you set W equal to 0, gravitational potential is constant. That means that matter perturbations must scale proportional to the scale factor. So if the scale factor grows, matter perturbations grow. That follows directly out of the Poisson equation because the matter density scales is 8 to the minus 3, so you plug it in here, and you see that delta m scales is 8. So this is interesting. The universe is expanding. The perturbation in the gravitational potential remains constant. So the matter must cluster a little bit more to compensate the stretching of the universe. You're putting particles further apart, which should decrease the gravitational interaction. So in the overdensities you must increase the clustering to counteract this dilution of the gravitational potential. So in the matter-dominated area the potential is constant, but the density perturbations grow. So this is important to realize because you may have an intuitive picture of gravity in the sense that when there's an overdensity you have a deeper potential, when there's an underdensity you have a higher potential. But there's this factor here, the a squared, the scale factor of the universe, that that slightly changes that picture. Okay, so constant gravitational potential does not mean constant matter perturbations. Okay, so now I have shown how to qualitatively how the gravitational potential evolves in time. Right. Then we use the Poisson equation to relate the gravitational potential, to relate matter perturbations to the gravitational potential. And without explaining the rest of the many more details, you then get a power spectrum for the matter perturbations in the universe. So first, remind you what is the definition. The power spectrum fundamentally is the amplitude of the correlations, of the two-point correlations in Fourier space. This question?
Yes. So I had a question about what happened when the dark energy starts to dominate, but I think I have my answer. I mean, from the equation I know that it would be oscillatory, and I think it's the case. So we see.
No, it's not oscillatory. No.
No. But if I put omega is -1,
yeah,
I get the equation for a.
Let's see. If you put omega equals to -1, this term just cancels, so you get an oscillation. Yeah.
No.
However, omega equal to -1 is a very special case because that's a cosmological constant which does not cluster.
Mm-hmm.
So this term is also not there. There are no perturbations. So you should actually be solving a slightly more complicated equation, namely a different one from this one, but one where you have two ingredients, so you have matter perturbations and a cosmological constant. And it turns out that the intuitive picture that the expansion rate slows down the growth of perturbations is true. Yeah. So you're right that if you just plug it in here, you don't get the right answer. That's a good point. Thanks for asking. But it's because this equation is not exactly applicable. Yeah, I'm oversimplifying things here in this point.
And I had another question.
Yeah.
This P of K is actually the same thing as the CAs that we, or the DAs we want.
Yeah, exactly.
So
it's the same, but in 3D instead of all sphere.
When we put like in the, we always do the power spectrum of galaxies in the, using the P of K and not the DA. Why? Is it just because we do not see something on the sphere?
Very good point. The short answer is that we're doing it wrong. We're doing P of K, but we should be doing C of L. And the reason is that, if you want a longer explanation, nearby the expansion rate is a linear function, because we're looking at small redshifts, so a Taylor expansion is fair to do, there's no error in there. And therefore it is straightforward to translate redshifts to distances. And if you change the expansion rate, that's just a linear rescaling of the distances. That's why actually you measure things in megaparsecs over h. That is to cancel out our ignorance of the expansion rate. So you can straightforwardly translate redshifts to distances, and you can even ignore the fact that we're observing on the light cone. So we can turn a two-dimensional observation plus a redshift into a three-dimensional picture of the universe. And that's why you construct a three-dimensional power spectrum. And the desire to do this comes from the fact that the fundamental theory also gives you a three-dimensional power spectrum. But you're absolutely right that fundamentally our observations are only angles and redshifts, so we should actually be doing a spherical coordinate decomposition, spherical harmonics and spherical Wessel functions. Yeah. So that comes to the point that this P of K is actually not the observable. So still, let me carry on with this. The power spectrum is it tells you what the correlations are in the three-dimensional field. And if it's a Gaussian random field, then the two-point correlation in Fourier space is given by the speed of k. But you could only measure this, as I tried to argue yesterday, if you can observe infinitely many universes and repeat the measurement of the position of two overdensities and infinitely many times. Then you can measure if they're really correlated, if the origin of these perturbations is really correlated. We only have access to one universe, so we can only look at the spatial, at the Fourier transform of the spatial positions, which is also a correlation function, but it doesn't relate to their origin. In this slide I put another quantity, so this figure actually, so this wave numbers here and power spectrum here. This figure comes from this review by Julien Lesmouk and Sergio Pastor, in which they describe massive neutrinos, and that's why I put this slide here. It shows the effect, I hope you can see the different colors, of massive neutrinos on the power spectrum. The black dashed line, the top line, is the matter power spectrum in the universe when there are no neutrinos present. The red solid line is a universe with only massless neutrinos. So no matter what scales you're looking at, they're the same as radiation when it comes to gravity. Not the particle interactions, but gravity. The green dashed line, which is here, is the matter power spectrum in a universe where there are neutrinos present and they have a significant mass. Significant in the sense that their fraction, they represent 1/10 of the matter content of the matter content of the universe. So you replace 1/10 of the dark matter and baryons with neutrinos. That's F nu equal to 0.1. Here's a green line. So that's the legend. So the correlation in the positions of galaxies is affected by the presence of neutrinos. And I didn't show neutrinos in the previous equation because, in fact, I didn't even show Boltzmann equations. I just showed the linear gravitational potential. But I will try to explain you in words, and I hope that in that way you can remember what it does, the impact of neutrinos on the matter power spectrum. So we saw that the dark matter clusters, and when the baryons are decoupled from the photons, they cluster just like dark matter does. Everything falls into the troughs of the gravitational potential. Photons, after decoupling, are just freely traveling around the universe. So they are there, they are present as energy density. So they contribute to the expansion rate of the universe. But because of their velocities and their lack of interaction with other matter, they don't cluster gravitationally. Because we're talking about linear perturbations, we're not talking about black holes, so the photons just travel through freely. They don't cluster, and they are present as a radiative ingredient in the expansion rate. That means that the expansion rate is slightly different from what it would be in a universe with only dust. The expansion rate is slightly higher. But the clustering of matter is given by only the matter, not by the photons. So because of the presence of radiation, the expansion rate is affected by different matter ingredients, different energy ingredients, than the clustering of matter. Clustering is only done by massive particles. The massless particles freely go around. So the growth of structure, the clustering of matter, is slowed down a little bit by the presence of radiation. Okay? If you have only matter, clustering and expansion rate are described by the matter and structure grows. If you replace a little bit of the matter by radiation, clustering is described by less matter and expansion rate is described by matter plus radiation. So the growth is slowed down. Now the point of neutrinos is that when they are massless and you replace part of the matter by massless neutrinos, you see exactly that they decrease the growth of matter because the amplitude in the matter perturbations on small scales is simply lower. And now if we give them a mass, the effect on small scales becomes worse because we take even more energy out of the dark matter. Because we can give them a mass, but because of the energy budget of the universe, we have to take it from somewhere else. And that's why the power spectrum is even smaller on small scales. And what unfortunately you cannot see very clearly in this picture, but I hope you trust me when I tell you, is that the transition from where they contribute as radiation to where they contribute as matter depends on the mass of the neutrinos. So actually, if you focus on this area, you see that the let's see, the red line goes away from the black line at a different point to where the green line does, but it's not convincing in this picture. But anyway, on larger scales, neutrinos do have a, not on large scales, but neutrinos have a mass. And they have a very tiny mass, so they have large velocities. And that's why if you focus on small scales, neutrinos have such high velocities that you should treat them as radiation. They don't cluster. So with massive neutrinos, tiny masses, on small scales, they are massive, but you treat them as radiation because their velocities are too high. They don't cluster. However, their velocities are finite. It's not the speed of light. So if you go to larger distances, you will see that they don't behave as photons. They cannot travel infinitely far. They cannot infinitely far is the wrong wording. They cannot travel as far as photons. So if you zoom out far enough, you can treat the neutrinos as massive particles. So if you look at wavelengths in your density perturbations that are larger than the distance that a neutrino with some finite velocity can travel, for those modes the neutrinos behave as if they are matter. So there the clustering of matter behaves as if all the massive particles are dust. So that's how large-scale structure actually aid in constraining the masses of neutrinos. Because for small scales, they act like radiation. For large scales, they act like dust. And there's a transition from one to the other behavior. And if we could observe this transition in the large-scale structure, cosmology can give a strong bound on the neutrino masses. And given the forecasts for future experiments like LSST and Euclid, there are actually hopes that cosmology will be the first with giving a lower bound on the mass of neutrinos. So far we only have upper bounds on the masses of neutrinos and an absolute lower bound coming from the oscillations of neutrinos. So we know that there is a lightest and a heaviest neutrino, and if you set the mass of the lightest neutrino to 0, you have a lower bound on the mass of the heaviest neutrino. That's where the lower bound comes from. And hopes are that cosmology, given this effect, can constrain neutrino masses to a tighter lower bound that lies above the absolute minimum that comes from showing that the lightest neutrinos masses. So hopes are cosmology does that sooner than particle experiments do that. Now about, okay, so this power spectrum here is going actually from very tiny case, very tiny wave numbers, so very large scales, to much smaller scales. And if you compare the x-axis, this one actually starts, it's a linear plot, so that's not very handy, but it actually becomes relevant at k roughly 0.0 a few, 0.02, 0.03, so that's somewhere over here. So it's before this bump in the power spectrum. These are the deepest observations that we have so far of the large-scale structure of the universe, of the distribution of galaxies. This is from the Wiggles experiment, which is whose main contributor is Australia, or maybe even the only. I think it's international, but it's mainly in Australia. They observe the positions of galaxies, turn that into a density field, assuming the galaxy is trained at a density field, and compute the power spectrum of the density field. So you get these data points with error bars. But let me say once more, that is the Fourier transform of one realization, of one image, one three-dimensional image, angles and regiments. The solid line, I think, is the theoretical prediction Well, now I see here that it has some angle, so it may actually be just a line from it. Should be theoretical prediction of the distribution function that gave rise to the galaxies. So it's not exactly the same, but they do, if the distribution comes from a Gaussian random field, they do measure the same thing. So positions of galaxies can help constrain the matter-power spectrum, and as I will convince you here, the matter-power spectrum is sensitive to the readings of the universe and to the theory of gravity describing the universe. This is the matter-power spectrum observed in different redshifts. So if you remember that the universe is a sphere around us and we live in the center, the previous slots showed the power spectrum at redshift of 0.3, 5, and 7. So these are different shells in this spherical universe. Okay? And where are we? Yeah. This is all linear perturbation theory. These are observations, and this is the fit to observations from linear perturbation theory. So far, it's been very clean and simple. All linear perturbation theory. However, are all quantities always small? And the answer I give you already is no. If you go to sufficiently small scales, and as a cosmologist, small scales are something that for an astronomer are still large scales. If you go to scales below, well, there's another typo. If you get to k larger than 0.1 h over megaparsecs, large k is smaller scales. So if you go to scales smaller than 10 megaparsecs over h, actually 2 pi times 10 megaparsecs over h, perturbations are no longer exactly linear. That is as much as saying that it's no longer a fluid that is slowly clustering, but the particles are actually crossing their trajectories and start, for example, entering orbits around the center of gravitational potential. And that means that halos of dark matter form, that means that galaxies form inside these halos, it means that stars form, etc. It's all very highly nonlinear processes. This happens at small scales. So some scales are already in that regime, where particles start orbiting gravitational potential. That means that in this regime, you can no longer describe the matter in the universe as a fluid, but you have to talk about the individual particles, or at least realize that your phase space is no longer, that your velocity field is no longer a single value, so your phase space has expectation value that gives possibility of different velocities at different places. So what does that look like? Here I have put dots with a Gaussian distribution, where actually they're all in a very irregular grid. This is a very early universe. This is a linear perturbation. In colors that you cannot yet recognize, I have marked in yellow overdense spots and blue underdense spots. Now if you let them cluster in time, like a fluid would do, they'll start moving, and it will be very fast. They will actually move towards overdensities. So this is actually a picture of the early universe. These are linear perturbations, and if you have some imagination, you may actually look at this and see that it's very similar to the cosmic microwave background. It's a Gaussian random field. Linear perturbations, particles cluster together, move towards each other, and form overdensities. But you see here already something's going wrong. We can watch it again. But let's focus on this point. Particles are all separated from each other on a regular grid. But at some point, they cross. You see that the particles that now are ending here started left of the particles that ended over here. And these particles actually started right of those particles. So the particles have crossed. That means that in this illustration, I have extrapolated beyond the regime of validity of the fluid approximation. This is no longer described by a fluid, because if I look at this point here, and I measure the velocities of my particles, I will get multiple answers at one point in space-time. And that is one indication that your fluid description is broken down, because a fluid is one velocity at each point. So we started with one velocity at each point, particles shall cross, and then they go beyond each other. Okay, now I want to explain to you how to simulate the nonlinear formation of structure. And I will do that without many equations, so will be difficult to formulate. I'll give it a try anyway. Linear perturbation theory breaks down when this happens. However, if you zoom out, if we just take the coarse average of this, you just have an underdensity here, and a growing overdensity here. So if you only consider large scales, this is still perfectly linear. If you consider small scales, you zoom in, you see that particles have actually started crossing. So if you go to small scales, you need a nonlinear description. Now, the simplest thing to do is, of course, take all these particles, put them in a simulation, apply Newtonian gravity to them, and let time evolve and see what happens. That is in fact what we do in cosmology. Newtonian gravity plus one extra very important term, which is taking into account the expansion rate. So you have particles in an expanding universe, you let them cluster under Newtonian gravity plus a friction that comes from the expansion. And now I want to try to explain to you what it really is that you're simulating there. You're not simulating very massive particles that are behaving under Newtonian gravity. Because what you're really simulating is tracers of the actual density field. And you're following their paths, and you're trying to follow what the phase space really does. So maybe I should show this slide later, but here I've taken the same dots. You see, it's exactly the same structure. Well, it's hard to see, but it is the same structure. Exactly the same structure, but now I put lines connecting the dots. So it's a grid of lines. Now if you play time, you see very nicely that this part is expanding, and here it's collapsing. But you can also see that the lines connecting the different dots hint at what the particles do that are between the dots that I'm simulating. So why do I do that? Let's simplify to a one-dimensional problem. Let me try to explain what the phase space is that you want to simulate. Here I put a large number of particles, I think it's 100,000, so by all means it's just a continuous simulation. At positions in arbitrary units, varying from 0 to positive and negative, from negative to positive. And on the vertical axis I put the velocity of these particles. So positive velocity means that the particle is moving in that direction. Negative velocity means that the particle is moving in that direction. I have given, on the red line, the infinitely many particles, I've given them a tiny density perturbation that is overdense in the center. I've given them 0 initial velocities, and then you see that they will start falling towards the center, and here they will start falling towards the center. But what happens if you let a marble roll in a potential trough? It will go through the minimum, overshoot, and because of the gravitational pull, will slow down and fall back again. It will oscillate around the center. So what do these particles do if you turn on time? You see that they increase their velocity towards the center. These increase the velocity towards the center and start moving towards the center. They overshoot the center, slow down. You see this velocity goes back to 0 again with this particle that we're following here. And the velocity turns into the other direction. It becomes positive and moves towards positive x. Crosses the center again, overshoots, and the velocity slows down again and becomes negative. Okay? So this is a one-dimensional illustration of the phase space. I follow the velocities and I follow the positions of my particles. Initially, it was described, could be described as a fluid because I have one velocity everywhere. So there are more conditions to be able to describe as a fluid, but let's focus only on that one. And at a later time, the particles cross the center of the system, and now, at point 0, I have multiple velocities. I have this velocity here, and this velocity here. Now it's no longer a fluid description. So if you want to simulate the formation of structure, individual particles, ideally you would do it with infinitely many particles, with infinitely high resolution, no problem with dynamical ranges of your numerics, and you get the true answer. Right? It's like taking a numerical integral with infinitely many steps. So if you want to know the real answer, ideally you would take this infinitely high sampling of your space. But we have a finite resolution. And that's why I put these blue boxes on the line. Because now imagine that we don't know what the red line does. But we have a very good gravity solver that, in spite of the fact that we have a limited resolution, does tell you where this point that lies on the actual continuous red line will go in time. So ideally, when you solve an n-body problem in cosmology, you're actually simulating a system with particles, like really atoms, and follow their motion. But we have limited resolution, so we only put the blue dots in. So this is a hypothetical situation in which we are capable of just simulating the blue dots and following their path in phase space. Okay? This is idealized. But I'm showing this because I want to convince you that in an n-body simulation, when you put particles in and try to simulate the logical structure of the universe, you are not taking an average of your space-time and putting that in a big box and letting that move. So when I go back to this movie, I have chopped my space-time into parts and put everything in dots. When you're doing an n-body simulation, you are not saying that this individual dot here is actually a point particle with all the mass that was in the grid cell around it. So I'm not saying that this is a 10 to the 10th solar masses object that is really moving around in my gravitational potential. Ideally, I want to pretend that this is just an infinitesimally small point that is tracing what the underlying phase space does. And the reason is that if you have infinite resolution, so I'm following these blue particles, but I have infinite resolution and I follow the red line, you see that remarkably, well actually it is, if you think about it a bit longer, it's not so strange, this sheet in phase space never breaks. Because I'm still talking about a continuous system, because atoms are so tiny that by all means it's a continuum of particles in space-time. So if I know the position of two particles that were initially neighboring in my phase space, and I look at a later time, they will still be, on this line, they will still be ordered the way they were. The point is just that the line is no longer a single value line. So the sheet in phase space doesn't tear. And that's why you should not think of these particles as point masses that have all the mass that is surrounding them. So in principle you could say, well, this particle here is just carrying all the mass that surrounds it because we have no higher resolution. No, you should think of the particle as just tracing this point of the phase space. And I know its neighboring particles in the initial initial configuration. So at a later times, if I know this particle position and I know this particle position, it should be such that all the particles that hypothetically were between the two are still between the two. Okay, and this is what it means to simulate tracers of the phase space. Okay, I'm trying to make this clarification of n-body simulations, because if you do observations of the latent large-scale structure, you will need information from n-body simulations, and it's important to realize that they're simulating the phase space and not just the masses of particles. So I skipped these slides. Well, so let me show you again. I have the individual dots here. When I plot it like this, you would think, you're tempted to think that these are really individual masses moving around. But if we draw lines between them and realize that particles that were initially next to each other in phase space will always be next to each other, you can understand what the meaning is of this phase space. So this initially, I don't know what number of particles in each cell, but this cell expands, so this becomes an underdensity. Other cells collapse and become lower density, etc. This is tracing.
So it may happen that one particle and then the next one, there's a line between them.
Yeah.
In the simulation, they will go to the same place again.
Yeah.
So the line is just a point.
Yeah.
But all the particles are not on the line, they are just elsewhere. The two endpoints of the line are on the same point, but the line that contains all the points in between, you have no way to stay.
No, exactly. And that's why finite resolution will never give the absolute continuum answer. So all you can do is do clever tricks to avoid these problems and realize that you just have a limited resolution of your simulation. Yeah. So, exactly in this image, what Richard is saying, that the line between these two particles could actually, because of whatever effect, could have a crazy shape that we can never infer. But in our simulation with finite resolution, we can only interpolate and infer where these are. And of course, it's basically saying that the interpolation may be wrong. Yeah. No, that's important to realize. So, when you look at the results of MO simulations, people sometimes compute power spectra at resolutions that are much higher than their initial setup was. So you should be cautious with that. That's what I want to warn you about as well. So why would you need to go nonlinear? Well, the point is that galaxies are highly nonlinear objects. They are virialized objects, which means that the particles are in orbit around the gravitational potential, and it has become a stable system. It has become a stable system where particles have crossed their trajectories, and it's no longer described by a fluid, but it's described in nonlinear dynamics. However, if you zoom out and you consider that the galaxy as an object, you hope that it does trace the linear density field on larger scales, because that's what we want to get access to constrain the theory of gravity. The point is that we need to make sure that this actually is true. And that's why we need to do body simulations with very high accuracy and putting in much more physics than what I talked about here, because I didn't discuss baryon physics, I didn't discuss galaxy formation. Because we need to figure out whether the galaxies actually trace the density field. Because if we want Euclid and SST to make sense, we need to understand what the relation is between the position of a galaxy and the overdensity of the field. So these are two very important body codes that are available on the market. You download them, compile them, and play with them. And then you get things like this. Yes, that's what I forgot. Yesterday I had a bad internet connection, so I wanted to download this video, and I think, yes, your internet is fantastically fast, of course. So, try to put it here. Is it visible? Yes? What we see here is a visualization of a Newtonian n-body simulation in cosmology, including baryons and the formation of galaxies and even explosions of AGN. Well, they're not visible in this visualization, but including the effects of baryons. So highly nonlinear physics, with the purpose of understanding how the structure in the universe forms. So this is from the Eagle simulation, which is a collaboration between Durham and Leiden and Heidelberg, I think, maybe in Munich, which is a very large setup, a very large cosmological simulation with very high resolution, such that you can resolve both the formation of large-scale structures, so the filamentary structure of the universe, and the formation of galaxies in those filaments. And then you can actually see whether galaxies form in dark matter overdensities or not. And clearly they do. So if I play this again, let's see, unfortunately it's too small to read, but I can guess what these two images show. This one just shows the density of matter. The different color coding shows how much matter there is in a point. And I believe this one shows either the temperature or the density of baryons individually. So let's play it again. Refuses. too bad, it won't play again.
But the universe forms only once.
Sorry?
The universe forms only once.
Only, yeah, exactly. This was our only chance to see it, and we have to do with it. Yeah, absolutely. The universe forms only once. So you see the particles cross their trajectories, cluster in the center, and baryons, however, exert a pressure, so it changes the formation of structure compared to the linear picture that we discussed previously. And here you see the orbiting of the individual objects.
This is of course with dark material.
Excuse me?
This is of course with dark material somewhere.
The dark matter in it somewhere. Yeah. So this is the total matter density, which is dark matter and baryons. Yeah. And this shows the baryon temperature. Yeah. Okay. I'm going slower than I thought. I thought I didn't have enough to tell you, but I do. So I hope I convinced you that nonlinear simulations are necessary. I just argue that we need to understand where galaxies form and how they form and if they really trace the underlying density field. Because then we can figure out whether our observations in the sky actually tell us how gravity pulled together matter. So we can test gravity and we can test how the dark matter was distributed. Another observable that comes from large-scale structure formation, and that is subject to nonlinear effects, is the baryon acoustic oscillation. And I want to explain to you in a few words what these are. And these few words are actually these, same peaks as in CMB. The baryon acoustic oscillations are the oscillations that we see in the cosmic microwave background. So, the early universe was a coupled baryon photoplasma. This was oscillating. So you have overdensities and underdensities, and depending on the scales you consider, the oscillation was in a maximally contracted state or a maximally expanded state, and there's also the phase in between in which it's maximally homogeneous. And then the photons decouple. So you have an oscillator that suddenly stops oscillating. So it's frozen in at a particular phase. And this phase will have an oscillatory shape, of course, like on the black board there. Photons decouple, there's no more pressure, so the oscillations stop, but the oscillatory shape is frozen in on the large-scale structure. These are linear perturbations, and then at later times, matter collapses in the overdensities of these perturbations. So galaxies trace out the galaxies trace out the perturbations of the total density of the universe, and this total density of the universe carries the imprint of these frozen-in oscillations from the past epoch in which photons and baryons were coupled. It turns out that in the distribution of galaxies on the sky, we can observe this typical scale. And here it's shown as a two-point correlation function as a function of co-moving separation. So this is in real space, not in Fourier space. And if you look at, for example, you consider a galaxy somewhere and you look at the chance that there's another galaxy at a distance of exactly 70 megaparsecs over h away from that galaxy, this function gives you the chance that there is one. And you see there's a tiny bump, there's a tiny peak, close to 100 megaparsecs over h. And this tiny peak is exactly the baryon acoustic oscillations. So I found a nice illustration somewhere on the internet. I'm sorry that I didn't put the source here, but if you, it just comes out of Google Images. This is an illustration of what the baryon acoustic oscillations look like. And what you should picture is a pond, water perfectly smooth, and you take a handful of rocks and you throw them at random positions all at the same time into the pond. Of course, where a rock enters the water, a ring of waves will start expanding around it. So the pond is everywhere equally deep, it's everywhere the same water. we can compute what the velocity of that wave is. I throw in the rock, I know the velocity of the wave, so at any later time, I know the radius of that ring around the place where the rock fell in the water. Right? Just the time times the velocity of the wave. If I throw in many rocks, around the point of each rock that fell in, a ring forms of exactly that radius as a function of time. So at a later time, I know that the waves in my pond, which also happens to be infinitely large and has no boundaries, so the waves never reflect back, it will be a superposition of rings around these rocks that I threw in the pond. That's exactly what the baryon acoustic oscillations look like in the cosmic microwave background and in the large-scale structure formation. Around every overdensity that was at a random but Gaussian correlated position, around every overdensity, a pressure wave once moved outward under the influence of the photon baryon pressure. So this wave travels a distance with a finite velocity that we can compute given perturbation theory. And in a finite time it travels a finite distance, and then at some point photons decouple. Pressure disappears, so the wave is frozen in. It's like you throw your rocks in the pond, and at some point you stop time. And the pond keeps that wiggly structure. So around every overdensity we have, in a sphere around it of 150 megaparsecs, or 100 megaparsecs over h, we have a overdensity of the pressure wave that goes out. So now you should imagine putting many rocks not in a regular distribution like, many overdensities not in a regular distribution like here, but in a Gaussian random distribution. It will still be such that at a later time there is a sphere around that overdensity which is overdense itself. So the chance of finding matter here is highly correlated with the fact that you have an overdensity here. And that is the characteristic scale of the baryon acoustic oscillations, the characteristic scale in the cosmic microwave background, which corresponds to a distance today of 100 megaparsecs over h, and in angular scales in the CMB it corresponds to 1 degree. So I know what the physical size is. In the CMB I observe it at 1 degree, and in fact we observe it in the galaxies also at a particular angular scale. In this figure, unfortunately, it already has been translated to the distance, but remember that we don't observe the distances, we only observe the angles. So, I hope that convinces you that it actually is a measurement of the angular diameter distance. If we measure this characteristic correlation in the galaxy distribution, then we observe an angular scale, we measure it at different redshifts, we have an angular measurement of that physical scale at different redshifts. So we're measuring the angular diameter distance once more. And this is a slide that I showed you in the first lecture, so we make a nice connection to that again. These are data points, ignore the orange ones for the moment, but focus on the blue and the black data points. These are different experiments, all Earth-based. So WOS is the baryon oscillation survey. Wiggles is the high redshift survey, which I showed previously also, which is in Australia. And this is the Sloan Digital Sky Survey. This is a US experiment. And the 60-degree field of view galaxy survey. At different redshifts, they measure the angular size of this typical perturbation in the galaxy distribution. Because galaxies form in the rings around the spots where I threw my rock in the pond. So at different redshifts, these are angular diameter distances. So the baryon acoustic oscillation, completely independent of supernovae distance measurements, give a very clear constraint on the expansion history of the universe. Baryon acoustic oscillations, therefore, are a very important ingredient in constraining dark energy. And what's important to understand is that this comes from completely different physics than when you look at the distances of supernovae. So we measure the distances of supernovae by measuring their intensity, or actually by inferring their original brightness, because it's related to the evolution in time of their brightness. Like supernova explodes and then dims again in light. So to understand supernova distances, the orange data points, you need to understand how a supernova works, which is a very highly nonlinear process and many ingredients going there. It's very difficult physics to solve. So you see a supernova, you want to infer what its original brightness was, and then you can use that as a luminosity distance. Independently of that, with linear perturbation theory, in the distribution of galaxies, you get a handle on the same quantity, the angular diameter distance. Completely independent physics, and they lead to the same preferred value of dark energy. So this is why large-scale structure formation is very important to understand, because it is independently a very important evidence for dark energy, independently of supernovae, and since the BAO want these dark energy, you can no longer say that the fact that supernovae need dark energy could be related to something else. For example, that the supernovae have different luminosities at different ages of the universe simply because the surrounding is different. That's no longer a sufficient solution to explain the supernova systems, because linear perturbation theory independently shows the angular diameter distance and needs dark energy. Now it's already 11:30 and I didn't just say anything about weak lensing, but I have 2 slides about that, and that's the end of today. So for the baryon acoustic oscillations, you need to understand that galaxies follow the density field, so you need to do simulations. And also, the physical scales of these baryon acoustic oscillations are close to the nonlinear scales. So linear perturbation theory is not the most accurate result. The same goes for weak lensing. So what is weak lensing? That's actually the only thing I'll try to explain what it really is. Galaxies, let's say that by approximation galaxies are circular. They're disks with a circular shape. Of course, if you observe it edge on, it will be an ellipse. But if you assume that their distribution and their orientation is completely random, then on average, if you look at the shapes of galaxies all over the sky, your average galaxy orientation will be a circle. Now, what we observe is not actually the original shape of the galaxies, because we observe the light that was emitted by the galaxy and the light traveled towards us. Light is, of course, subject to gravity. So light gets lensed by structures that lie between the light source and us, the observer. And depending on the shape of the objects between us and the source, the light gets curved in different ways, and a finite shaped object gets squeezed in different ways, squeezed or rotated. So initially, the galaxies at their emission may have had a distribution that on average gives a circle. But because of the lensing of light, we can see that in different directions there may be a correlation between the orientation of the galaxies in that direction, because of the lensing of the light. And that is weak lensing. Of course, we only observe one sphere, only a function of 2 angles. So in principle, we measure an integral of the shape of the gravitational potential along the line of sight. We only observe this patch, and the shapes of these galaxies and the distribution of their shapes is subject to the integral of the gravitational potential along the line of sight. And then, of course, you can make maps that look like these. Unfortunately, the axis fell off, but this is just the angle in one direction, this is the angle in the other direction. And these lines trace the preferred orientation of galaxies on the sky. So if initially galaxies were randomly orientated, it's an important if statement, if they were randomly orientated, then and there's no lensing, then on our sky they should still be randomly orientated and there should be no preferred directions. If you simulate what it looks like if there is weak gravitational lensing, then there will be preferred directions of the galaxies in their orientation. And you can turn that into a map. And of course you can decompose the map in, just like in electrodynamics, in E modes and B modes. That means modes that are the divergence of the scalar field and modes that are divergence free. But they have a rotation, have a curl field. Right, so what I will not show any equations anymore about this, but I want to at least have explained to you what the effect of weak lensing is. Initially randomly oriented galaxies on our sky have correlations in orientations. But this is another reason why it's important to do simulations. Because it turns out that the initial distribution of the orientations of galaxies is not entirely random. Galaxies tend to align with the tidal field. The tidal field is simply the second derivative of the gravitational field. The gravitational potential may be steeper in one direction than in the other direction. And the galaxy, when it forms, tends to align with the preferred direction of the gravitational field. So if I have a filament somewhere, so a long beam of dark matter, galaxies that form close to the filament will be actually aligned with that filament or exactly anti-aligned. Which one of the two it is doesn't really matter, but they have a preferred direction because of the underlying structure. And you need to take that into account when you try to decompose the map of orientations of the galaxies on the sky, because you need to take into account that these correlations are not only given by the integral of the gravitational potential, but they're also given by the intrinsic alignment of galaxies. And that's the difference between intrinsic alignment and lensing alignment of the galaxies. So this was very qualitative. I didn't show any equations, but I hope that I convinced you of two observables in large-scale structure, namely the baryon constellations and the weak lensing, which traces the matter density field. And I hope I convince you that you need to understand the nonlinear dynamics of the structure formation of the universe to use these observables to infer something about the universe. One thing I didn't just say is that, of course, you can cut your observations in different redshift slices because we observe these galaxies as much as we do observe those. So if you only look at the preferred orientation of galaxies in different redshifts, then you are actually sampling the higher end of your integral of gravitational potential. That's called weak lensing tomography. Because the integral so let's say you have a density field, and we are the observer here. And we have redshift 0.1, 0.2, 0.3. A galaxy that lives here, for us, traces the integral. Let's put it very schematically, it integrates from redshift 0 to redshift 0.3. And then some function of the gravitational potential is a function of redshift. So if we look at all galaxies that are here and they have some preferred orientation, their correlation is subject to this integral to 0.3. If you do it at redshift 0.2, we observe galaxies here, and we only look at galaxies close to here, then we're tracing this integral at 0.2. Okay, so you're sampling this integral at different higher bounds, and that may give you extra information about the gravitational potential and the way it grows in the history of the universe. So I didn't put a concluding slide, but therefore let me put up the outline, because that's basically the conclusion. So what have we seen? We have seen the scales in large-scale structure. We've seen how linear perturbation theory works and how it shows us how the baryon constellations form. We've seen that an understanding of the nonlinear formation of structure is necessary, and that it's necessary especially to understand how galaxies form and if they trace the density field or not, and how weak lensing works in effect. And how did I convince you that these, again, are very important ingredients in understanding the space-time of the universe, the formation of structure, and the theory of gravity that describes the universe. That's all I wanted to say today. So, are there questions?